Hi everyone, welcome back to Algebra 2. Today we are on lesson 2 or 12-2, conditional probability. I believe this is page 200 or 552 in your volume 2 workbook. If you don't have your volume 2 workbook, you'll see the link somewhere close on this page in Canvas. Somewhere close to this video, you'll see the link to the pages, or you can just take notes on your own paper. But what we'll be talking about today is something called conditional probability. Conditional probability is where you're looking at probability, maybe not for an entire group, but for a subset of a group. So you'll see this notation, probability B line A. The way that you say that out loud is the probability of event B happening given that event A has already happened. So it's kind of like a subset of the whole group. You're just looking at one subset and then the probability of something else happening within that subset. So the first example deals with that. So here we have, let's say these are members of a high school, and then our high school is kind of subdivided into the drama club, the science club, the art club, and then further subdividing into sophomores, juniors, and seniors. Apparently freshmen are not allowed in these clubs. I don't know why freshmen aren't listed here, they're just not. But anyway, what we're asked for is what's the probability that a member of the drama club is a sophomore? So they're not saying what's the probability from the entire chart. They want to know just out of the drama club. So given that we're only looking at the drama club, what's the probability that that person is a sophomore? So I'm only interested in the drama club here. Now this table is not on your workbook, so you'll probably want to pause the video and copy it down. So that way when you go back and look at your notes, it will make sense. But yeah, add this table to your notes. So we're only interested in the drama club. Notice there's 17 people total in the drama club. So what's the probability that the person from the drama club is a sophomore? Well, this right here is also our denominator. So remember, for probability, it's number of favorable outcomes over the number of total outcomes. Well, in this case, our total outcomes would be however many people are in drama. So there are 17 people in drama. So the probability of the sophomore in the drama club would be 3. So 3 out of 17. For part B, what's the probability that a sophomore is a member of the drama club? So in other words, let me see if I can zoom out a little better so we can see everything at the same time. There we go. What's the probability that a sophomore is a member of the drama club? In other words, what's the probability that given someone is a sophomore, that they're in the drama club? So this time, I'm interested in the sophomores. Come on, erase. So this time I'm interested in the sophomores, which is this subset. So probability drama given sophomore is, let's see, there are 36 sophomores total. And then 3 of those are sophomores. So 3 out of 36. 3 over 36 does reduce to be 1/12. Is the probability that someone is a sophomore given they're in the drama club the same as the probability that someone's in drama given that they're a sophomore? No. Not the same. 3/17 is not the same as 1/12. And so the reason that these are not the same is we're looking at different subsets. So one, we're looking at the number of sophomores altogether and however many drama people are, how many sophomores were in drama versus how many sophomores were in drama versus how many drama people were in the sophomore group. So then you'll be asked to figure out, using conditional probability, if events are independent. So just a reminder, independent events are knowing that the probability of one event is not the same as the probability, doesn't affect the probability of the next event. So let's say if I were to pick a card out of a deck and take that card away, knowing whatever card that was first, if I don't put that back in the deck, it is going to affect the probability of the second one. Those would not be independent events. Well, now we also have another test for independence that I can use conditional probability for. So if I've got two events and they're independent, then the probability of B given A is going to be the same as the probability of B, and the probability of A given B has to be the same as the probability of A. In other words, whatever subset you measure that event in is going to have the same of that small group for the whole. So whatever, no matter what your denominator is, you'll have like equal fractions. So like maybe you'd have 4 out of 16 versus 25 out of 100. Those would be the same. So let's see. Let's look at an example where we have to look at independence. In example 2, now in your example 2, you only have the try it part that I have right here. You could add this first part from your notes, or you can just watch the video and take notes from it, but let's look at it. But I'm going to zoom in. Okay, we have a table below that shows the vehicles in a parking garage one afternoon. A vehicle in the garage will be selected at random. Let B represent the vehicle is black, and let V represent that the vehicle is a van. So B is a black vehicle, and V is going to stand for van. And we need to know, are the events B and V independent of each other? Well, first of all, let's just find the probability of each event. So the probability of B, probability that we have a black vehicle. So let's see, black would be all of these vehicles. There's 6 black cars, 3 black vans, 4 black pickups. Altogether, there are 13 black vehicles. So the probability that we'll have a black vehicle just in general, 13 out of 22. Okay, and then what's the probability that we get a van? Okay, probability of a van, let's see, here's my vans. No red, no white, but there's 3 black vans. So 3 vans out of 22 total vehicles. Okay, so we want to know what's the are van and black independent of each other. So first of all, let's find this probability. The probability that it's black given that it's a van. Okay, so we know, so what we're saying is, okay, we're only going to look at the vans. What's the probability that's black? Okay, only look at the vans. Probability that's black. 3 out of 30, so 1. Okay, so it's definitely going to be black. So does the probability of, let me see, we know it's a van. So since we know it's a van, does that affect the probability that's going to be black? Yes, because the only vehicles that are vans are also black. So are these independent? No, not independent. Now, if the probability of black given a van would have been 1, or sorry, would have been the same proportion right here, saying that it could be a van, it could be a car, it could be a pickup, no matter what, there's an equal proportion of black vehicles being represented. Saying like this proportion right here would be like, okay, well, there's 3 out of 22 vehicles or 13 out of 22 vehicles that are black. Well, then in each subgroup, there should be an equal proportion of black vehicles. There would be 13 out of 22 black cars, 13 out of 22 black vans, 13 out of 22 black pickups. Then we would say that those events would be independent. But here they're not, because if I know it's a van, then I kind of automatically know it's going to be black because all the vehicles are black. Now, let's look at the example that you guys have. Again, this table is not in your notes, so you probably do want to add it so that your calculations will make sense when you go back to look at them. Let R represent selecting a red vehicle. So R is going to stand for red. Helps me by writing it down. And C is going to represent car. Are the events R and C independent of each? Independent or dependent? So first of all, let's find the probability of R. Okay, so the probability of R, red cars, there are 7 red cars out of 22. Okay, the probability of a car. There are 11 cars out of 22, which is a half. Okay, so are these events independent? Well, first, let's find the probability that it's red given the car. Okay, well, given that it's a car, there's 11. Red, 5 out of 11. So I need to compare. Are these the same? 5 out of 11 the same as 7 out of 22. Because remember, for something to be independent, and these proportions are going to need to be the same. So here we go. If probability of B given A is the same as probability of B, it has to be equal, exactly the same. Well, is R given C 5/11 the same as R? Nope, not the same. So they're not independent. Part B, not independent. So that would make them dependent. These events are dependent. Then for example 3, example 3 only gives you the try it part of the question. So you do need this information and you do need these survey results. So to take a second, pause the video, write down these survey results. Okay, so then also on this one gives kind of a lot of layers. There's a survey that was done and they asked 2 questions. They asked students, are you going to attend a concert or not attend a concert? And then they asked them another question, are you a fan or are you not? And so then they've given me this data. It's kind of partial data. So it's going to be up to me to put it together into the bigger picture. So I can see it in the bigger picture if I think of the questions that they asked. And since it looks like they asked the question first, like, are you going to attend or not? And then those who planned to attend, those who planned to didn't, then I'm thinking they probably asked fan or not next. So I'm going to go with this first question. Did they attend or did they not attend? And let's look at the probabilities of those first, and then we'll come up and answer the second question. So what percent of students plan to attend? Well, it says right here that 70% of students plan to attend. Now, this is information from the book. It just didn't get printed in your workbook. So you do need to add it like it was given to you originally. So I'm going to write that on this little branch right here. 70% plan to attend. And who did not? 30% plan to not. Now, whenever you have it, this is called like a probability tree or a decision tree. The probabilities on each branch need to add to 100% because it's like you're asking one question, and so like everyone needs to respond. So 100% of people need to respond. It looks like they did, 70%, 30%. All right, then of those who attended, 80% of those students are fans of the band. So of those who attended, 80% are fans. So 0.8 on this branch. And so if 80% were fans, then we can assume that 20% were not fans. And that allows me to have 100% on this branch. Then of the 30 people who will not attend, 30% who will not attend, 25% of those people are fans. Maybe they just had homework that they had to do and they couldn't go. And then 75% I can assume to not be fans, because then that would add to the 100%. So then this question, what's the probability that a surveyed student plans to attend the band's concert and is a fan of the group? So surveyed student plans to attend and is a fan. Looks like it's this pathway right here. So to get that probability, I can just multiply those two numbers together. So I can just say that I'll do 0.7, 0.70 times 0.80. Ooh, that's times 0.80 equals, I'll multiply those two together. And get 0.56. So 56% chance that a student plans to attend is a fan of the group. Okay, so then this next question, what's the probability that a surveyed student plans to attend but is not a fan of the group? So then I can look at this and be like, okay, plans to attend but is not a fan. Okay, so that would be plans to attend and is not a fan. Maybe they're just going to hang out with their friends. So that would be the second pink pathway here. So I can multiply 0.7 times 0.2 to get 0.14. 14% chance that they plan to go but are not a fan of the group. I'm just double checking my math here. Okay. Now, where does conditional probability come into play? Well, what about this? What if I ask you this question? What's the probability that they will attend given that they're a fan? So in this question, I'm not asking you first whether they attend or not, like I did here. This is looking at, are they going to attend or are they not? And then I would ask, are you a fan or not? Here I'm saying, of all the fans that are there, what's the probability that they're going to attend? So that means I need to consider those who will attend and those who will not attend. So let's first look at this. So first of all, I need to figure out the probability that they're just a fan, because that is what this denominator is saying. Well, we already know they're a fan. Well, I don't have that information up here. I don't know what the probability is that they're a fan. So first of all, let me find what's the probability that they're just a fan of the group. Well, if I look on my chart here, the fans are right here and right here. People who will attend and people who won't attend. So attend and are fans, we said that was equal to 0.56. And then they're still fans, but they will not attend 0.3 times 0.25. So 0.3 times 0.25 is 0.075. Hold on, my pen is really laggy. So probability that they won't attend and they're a fan is 0.075. You just multiply the 0.3 times the 0.25. So that would give me two paths of being a fan, whether or not they attended. So the total probability that they are a fan, you add this 0.56 plus the 0.075 to get 0.635. So the probability that they're a fan is 0.635, which I can add to be my denominator, 0.635. Okay, so then what's the probability that of all the people who are fans, what's the probability that they're going to attend? And remember, we're only looking at the probability of those that are fans. So the probability for the attend would mean they would have to be attend and also be a fan, which would be that 0.56 right there. So then I'll divide the 0.56 by 0.635, and I get 0.88. So out of all the fans, the probability that someone would attend would be 88% chance.